My name is Sai Prapal Reddy Totapalli, and today I will be presenting my project on predicting the electrical energy output of a combined cycle power plant. In this presentation, I will cover the modeling approach, model building, model evaluation, and model interpretation. The task at hand is a regression problem where we aim to predict a continuous target variable, the net hourly electrical energy output. Our dataset contains 9,568 hourly average ambient environmental readings with the following features: temperature, ambient pressure, relative humidity, exhaust vacuum. Before I start the problem, my approach here was to look at the dataset. So I wanted to check the data types and the null counts. Then I went ahead and did the correlation matrix. So I clearly found out that temperature and exhaust vacuum are highly correlated with the energy output. And since this is a regression task, the and it has a very limited features, I'm going to consider all the features for this, and I'm going to use linear regression and random forest regressor for the models and have split the data as 20% for the testing and 80% for the training. For the model building, like I said, I started with splitting the data into training and test sets. Then I wanted to use the five-fold cross-validation as my validation strategy and compare the linear and random forest regressor. Why did I choose those? Linear regression is simple and interpretable and assumes a linear relationship between the features and targets, whereas random forest regressor handles complex and non-linear relationships. So that is why I chose these two models. Coming to the model evaluation. To evaluate the models, I'm going to consider mean squared error and mean absolute error. The mean squared error for the linear regression is 20.27, whereas mean absolute error is 3.60. For the random forest regressor, the mean squared error is 10.54, whereas the mean absolute error is 2.33. These results were calculated on the test set, which provided an unbiased estimate of the model performance. Clearly, the random forest regressor is the winner here in both the metrics, be it either mean squared error or mean absolute error in the model interpretation. The random forest regressor showed better performance, so I selected it as the final model. To understand the model better, I analyzed the feature importance. And in this graph, you can see that the temperature had the highest impact on the energy output prediction, followed by exhaust vacuum, ambient pressure, and relative humidity. In conclusion, the random forest model provided a more accurate prediction of the power plant's energy output compared to the linear regression model. Understanding the key contributing factors such as temperature and exhaust vacuum can help in optimizing the power plant operations. And I've used the Google's Colab to perform all these computations and run my models. And thank you very much for watching this presentation.